All right, hello. I decided that I wanted to make a video going through one more example of the initial rate method, okay? I'm doing this not necessarily because I thought things went poorly today in class, but mainly just as an extra resource for people that would be interested in watching it. I know not everybody's going to watch it, but there are several of you that would be interested in this type of thing, so I think it'll be valuable. And my goal is to make it relatively short, so that even people like Eric can make it through the entirety of the video before they get bored and click off to something else. Okay, so we are asked to determine the experimental rate law for the following reaction using the data below. Okay, and I've picked some pretty simple data here. Okay, some nice whole numbers to make the math extraordinarily simple. Okay. The concepts are going to apply regardless of what the numbers are. But I'm hoping that, with some nice, easy numbers here, we can focus more on the concept rather than the mathematics. Okay? This is the reaction, some sort of really simple, halogenation of this hydrocarbon. I don't know what's going on here. Doesn't matter. Okay, let's see here. So we've got 3 trials. Okay? The general form of the rate law, let me see if I can get a little fancy here. Okay, so the rate is equal to the rate constant K times the concentration of the first reactant raised to a power N. I'll include that in just a second. And then we have a second reactant, HBr, and that's going to be raised to another power, which will be M. Okay? So let me go ahead and see if I can include those exponents here. Okay, let me try that again here. N and M. Okay, all right, that doesn't look too bad. Okay, so we're trying to figure out what N and M are. And we're actually going to go one step further. We're going to see if we can figure out what K is as well. Okay? Okay, so the first thing, let's see if we can figure out N, okay? So what we're trying to do, right, is we're trying to figure out what the order of the reaction is with respect to this reactant, C5H10. We are trying to determine, does changing the rate, does changing the concentration of C5H10 influence the rate of the reaction, right? If it does, how much does it influence it? Right? Okay, let's take a look. So we want to look for 2 trials where this concentration changes, but the other one remains constant, right? Because we don't want to add in additional factors here or additional variables when we're not really concerned with this at the moment. We'll look at it in a minute, but we really just want to focus on 2 trials where this changes while this does not. Okay? And if you look here, Trial 1 and Trial 2 will give us an opportunity to do that. Okay? The concentration of C5H10 changes from 2 to 4. So, in other words, it doubles. Okay? The concentration of HBr remains constant. Okay? So, what that means is that any change in the rate is wholly induced by the change in this concentration. It cannot possibly have anything to do with this because this remained constant. Okay? So take a look, right? The rate doubles. Right? Goes from 10 to 20. So this is what a first order situation looks like. Okay? When you double the reactant and the rate doubles, that's first order. If you were to triple the reactant and see a tripling in the rate, that would be first order, okay? Take a look at the rate law, okay? What this is saying is that if I times 2 this, I times 2 this, right? That only happens if you're raising this thing to the first power, right? If it's raised to some other power, like 2 or 3, then times 2 is not going to give you a times 2. It's going to give you a times 4 or a times 8, right? So times 2 and times 2, the same multiplier on the concentration and the rate, that is what a first order situation looks like. Okay? We just need to get familiar with what these situations look like so that we can apply them in the context of a problem. Okay? Okay, so using trial 1 and trial 2, we can determine that the reaction is first order with respect to C5H10. Okay? Now, let's switch colors here, and let's look at HBr. Oh, that's not a good color. Let's try this one. There we go. Let's look at HBr. Okay? So, we're doing the same thing but in reverse, right? Now we want to find two trials where this is held constant, but HBr changes. Okay? Well, look here. Held constant, HBr changes, right? So trials 2 and trials 3, trials 2 and 3 are going to be the ones that I want to look at. Okay? Now, look at this. The concentration of HBr doubles, right? 2 to 4, and the rate doubles. Okay? This is first order again. Okay? So this is what first order looks like. Okay? So in this case, the reaction would be first order with respect to both of these. Okay? Now, I just for a second want to talk about what you would see if something was, say, 0th order or second order. Okay? So just humor me for a minute. Okay? Now let's say this was 0th order. Okay, let's say the m was 0, right? What would we expect to see in the data? Okay, well, if I change the concentration in HBr, if it goes from 2 to 4, what would I expect the rate to do? Think about what it means to be a 0th order reaction, or for something to be 0th order. What that means is that this concentration has 0 impact on the rate, right? It goes away in the rate law, right? If something is 0th order, here's what we would say, right? We would say that the rate is equal to K times the concentration of this first reactant. Oops. This is to the first power, right? But then if this thing is to the 0th power, right? If this is 0 order, then this goes away, right? This is just 1, right? So if something is 0th order, it means changing this reactant, changing this concentration, does not influence the rate at all. So if m were 0, if that were 0th order, then this would do nothing. It would go from 20 to 20, right? It doesn't matter what you do with these numbers here, with this concentration of HBr. It's going to be 20 100% of the time, right? It literally doesn't matter. Okay, so that's what we would expect with a 0th order situation. Okay, now let's change it up for just a second. Okay, what if it was second order? What would we expect to see in the data? Okay, if we double the rate, if we double the concentration of HBr, I should say. Okay, so if we go from 2 to 4, what would we expect to see with the rate? Well, take a look. We would be doubling this, but then that would be getting squared, okay? So we'd be doubling it, and then it gets squared. So it's times 2 squared, which is actually times 4, okay? So that's what we would expect to see in the data. We would expect to see a times 4 multiplier with the rate. So this would go from 20 to 80. Right? That's what we would expect to see in a second order reaction, okay, or if something was second order with respect to HBr. Okay? Turns out though, turns out that when you take a look at this data, the data that we are presented with in this table, it ends up being first order with respect to both. Okay? That's fine. Okay? So the overall rate law, I should say, is K times the concentration of both of these reactants, each raised to the first power. So I'm not even going to write that exponent. Okay, so that's equal to the rate. Okay, cool. Now, one last thing I want to do. You can then, once you have this, right, once you have determined the orders, what you can do is you can go back and you can solve for k. Okay, so you can actually solve for the numerical value of that rate constant. My coffee is like exceptionally hot. Goodness gracious. Okay. So yeah, you can use any of these trials. Okay, let me go through here and erase all of this stuff out of here. You can use any of these trials to determine what this value of k is. Okay, all you have to do is plug in these three pieces of information. Okay, we have spots for those three things. We have the concentrations and we have the rate. Just plug this stuff in and figure out what k is, right? So I'll use trial 1, all right? So k times 2 molar times 2 molar is equal to 10, here we go, molarity per second, or moles per liter per second. Okay, so I just need to solve for k. Okay, well, let's see, let me combine my two rates here, just multiply these by each other. So let's see, I have k times 4 molar squared, or moles squared per liter squared. This would be equal to my 10 molarity per second. Looks like I need to divide both sides of my equation by 4 molar squared. Okay, so this is going to isolate k. Now I realize that this looks really nasty. Okay, it does look nasty. It looks nasty to me. Now the number is not that nasty. 10 divided by 4, right? So that's what, 2.5? All right, so the number here is 2.5. The units obviously look kind of not so nice, right? So, you know, I don't want to make the video about the units. Okay, we already talked about how to find the units of k given different orders of reaction. I believe what this ends up being, one of the molarities ends up canceling here, and so you have the molarity in the denominator, or the moles part in the denominator, along with the seconds. The liters are in the numerator, so it's this, okay? Liters per mole second, or liters per second mole, okay? And this is your value of k, okay? 2.5 with these units here. All right, so that enables you to build sort of the true rate law, okay, with all of the bells and whistles. The rate of the reaction is equal to 2.5 liters per mole seconds times the concentration of C5H10 raised to the first power times the concentration of HBr raised to the first power. Okay, we're only at 13.5 minutes, so I think I've got time to mention one last thing. When you get to this point, when you know what k is and you know what the orders are, right? First order and first order. What you can then do, and what you are asked to do in a couple of situations in the problems in the book, they are going to give you new data. They're going to give you new concentrations, and they're going to ask you what is the rate. All you have to do is plug them in, okay? So they're going to give you some new initial concentrations, and they're going to ask you what is that initial rate, right? Just plug them into the rate law that you have developed given all of this data, okay? That's it, all right? So I think at the end of the day, that should get you through everything that you need to be able to do for those problems. Obviously, we will take some time at the beginning of the day on Wednesday to talk about some of these. I'll be more than happy to go through an example or two, but we won't be able to spend the whole day on it. We do have to move into 5.3. You know, we obviously have to keep moving along through the content, right? So hopefully, with this video now, you have you have some more confidence in being able to deal with these types of problems. These are the initial rate problems, right? Method of initial rates. We'll look at something just a little bit different with 5.3 starting on Wednesday. Okay? All right. Thanks for watching.